Welcome to the 2022 Ingenium Professional Development Seminars. On behalf of Engineers Geoscientists Manitoba, my name is Siwen, and I am a member of Ingenium Task Group, and I will be the moderator for this session. Before we start today, I'd like to acknowledge that the association office and the majority of its practitioners are located on Treaty 1 territory and the original lands of the Anishinaabe, Cree, Oji-Cree, Dakota, Inuit, and Dene peoples, and on the homeland of the Métis Nation. Many generations has arrived to our province and contributed to its development, but we must not forget that this land, indigenous land, has been inhabited by indigenous peoples from the beginning. Those first people called this area home for generations and thrived, took care of the land, and developed unique ways and methods of design to survive in our province's harshest conditions. The province's original engineers and geoscientists. We respect the treaties that were made on these territories, and we acknowledge the harms and mistakes of the past, and we dedicated ourselves to move forward in partnership with indigenous communities in a spirit of reconciliation and collaboration. Throughout today's presentations, we encourage you to send any question you may have for the presenters via the chat box. Please note that this presentation is being recorded and will be available through the Ingenium Hub from tomorrow until January. It is now with my great pleasure to welcome our first presenter for today, Brian Wilcox, who is joining us from Canadian Nuclear Laboratories. Brian, it's over to you.
Hello, and thank you for joining the session today. I'm really excited to talk to you about the decommissioning and environmental remediation of the Whiteshell Laboratories site. Feel free to type in questions at any time during the presentation, and I will answer them at the end. Let's get going. Just to start with a quick overview of the presentation. I'm going to talk to you a little bit about my company, Canadian Nuclear Labs, the history of the Whiteshell Laboratories research facility, our closure strategy for that facility. What is decommissioning and environmental remediation? I'll talk to you a little bit about some of the notable projects that have been completed and are underway. I'll talk to you about how we protect the environment and the public while we're doing the decommissioning. And then, as I mentioned, we will talk at the end about any questions that people have. First off, we seem to love our acronyms in the nuclear industry, but it can be confusing sometimes. So I work for CNL, Canadian Nuclear Laboratories. We're a contractor to the Government of Canada, and our job is to manage all of AECL sites and perform the decommissioning and waste management and the science work that occurs there. Atomic Energy of Canada Limited, AECL, is the federal crown corporation that owns the sites and is responsible for the liabilities there. CNL and AECL have a contractual relationship called GOCO, government-owned, company-operated. But there's another acronym in the nuclear family too, CNSC, the Canadian Nuclear Safety Commission. They are the independent federal regulator responsible for regulating all nuclear materials in Canada. CNL is able to operate and decommission because we have a license from the CNSC. I mentioned CNL manages several sites. These exist all across Canada. Our main site is called Chalk River Laboratories, located near Ottawa. It's Canada's national lab for the peaceful and innovative application of nuclear technology. It's home to the NRU reactor, which for over 60 years produced medical isotopes that diagnosed or treated millions of people annually in over 80 countries around the world. The Port Hope Area Initiative, located near Toronto. This is the government's commitment to clean up historic waste associated with radium and uranium processing that was done by El Dorado Nuclear, a former Crown corporation. There are also prototype reactors. Canada built prototype and legacy reactors in Whiteshell, at and near the Chalk River site, at the Bruce Power site northwest of Toronto, and the Gentilly site in Quebec. CNL manages all of these sites and is in the process of performing decommissioning. Shown in Northwest Territories on the map, the northern transportation route. So CNL manages low-level waste sites across Canada on behalf of the government. We have successfully completed projects in Ontario, British Columbia, Alberta, and the Northwest Territories. This typically includes radium mining in the north to other historic sites where radium dials were fabricated. Whiteshell is located about 100 kilometers northeast of Winnipeg near the town of Pinawa. At one point, Whiteshell was Canada's largest research facility in the West. The rest of this presentation will dive into what's happening at the Whiteshell Laboratories site. So CNL has three strategic priorities. Number one, contributing to the health of Canadians. A really exciting project that's underway is called Targeted Alpha Therapy, where actinium-225 is being researched to very accurately target cancer cells. So that gives you a sense of what that strategic priority is about. The second one is clean energy for today and tomorrow. This is all about developing clean energy solutions, including small modular reactors, hydrogen technology, and advanced fuels. And finally, the third strategic priority is restore and protect Canada's environment. This is the strategic mission that the Whiteshell Lab project falls under. Ultimately, this priority means that CNL will restore and protect Canada's environment by reducing and effectively managing nuclear liabilities. CNL is tasked with decommissioning and environmental remediation and establishing long-term waste solutions to reduce or eliminate legacy hazards. As I mentioned before, CNL is accountable to Atomic Energy of Canada Limited to do this work, to do it safely, and to reduce costs and financial risk for Canadian taxpayers. So as I mentioned, the Whiteshell site, the Whiteshell Laboratory site, is approximately 100 kilometers northeast of Winnipeg, and it's about 10 kilometers west of the town of Pinawa, a beautiful area if you ever had a chance to get out there. It's located just downstream on the Winnipeg River from the Seven Sisters Hydro Dam. And most of the site is located in Treaty 3 territory. That's the east side of the Winnipeg River, but it has some land on the west side, which is technically Treaty 1. The site covers an area of 43,375 hectares. This is approximately 11,000 acres. In the photograph here, you see the main campus looking eastward with the Winnipeg River in the foreground. The site is serviced with domestic water, processed water, fire water. It has storm drains, domestic drains and sewers, above and underground electrical distribution, and a fiber network distribution. Essentially, this site is a standalone community with complete with security, fire protection, and its own lagoon system, as can be seen in the upper left. Some of the notable facilities that you can see in this photograph, in the middle with the green indicator is Building 100. This is the WR1 reactor. There is a very large radioisotope laboratory labeled as B300, Building 300. And in orange, there's a water collection and treatment facility called Building 200. A bit difficult to see in this photograph, but in the very top left corner, there's also a waste management area and a non-nuclear landfill on site. And I'll show you better pictures a little bit later in the presentation. So why is Whiteshell Laboratories here at all? I mean, it was established in the late 1950s, early 1960s as part of the Government of Canada's expansion of nuclear research facilities. At its peak, there were close to 1,400 employees working on site. As I mentioned, it was the largest research facility in Western Canada. The picture you see here shows the building that houses the WR1 prototype reactor. That reactor was built to test the concept of using an organic cooled reactor as composed to water cooled, and to test different fuel types and different configurations. The Whiteshell site and the nearby underground research laboratory, which is now fully decommissioned, also led the development of the deep geologic disposal approach for spent nuclear fuel. This garnered collaboration from many countries around the world. Whiteshell also delivered extensive power reactor safety research, including developing hydrogen recombiner technology and performance studies on materials and components. So Whiteshell has a history of contributing extensively to nuclear research around the world. So CNL's mission now at Whiteshell, now that all of the research has come to conclusion, is to fully decommission the site and achieve closure. This is a very aggressive but a doable plan that is targeting 2028 to be completed. This photo shows the main laboratory area from the south now, as opposed to from the west, as I had shown you before. While some decommissioning has occurred, and sorry, this goes back to 2015, which kind of gives you a baseline of the site. Now, some decommissioning had occurred prior to this date, but this is when the government of Canada privatized the site operations and converted it to that government-owned contractor-operated model that I mentioned. This really was intended to bring international experience in decommissioning to CNL and to help transition from a research lab to a decommissioning project. This photo shows the decommissioning process that's been accomplished up until about current time here in 2022. We've already decommissioned over 40 buildings on site, and this includes a variety of laboratories, storage buildings, a decontamination center or water treatment facility, and numerous support buildings. So all of those buildings that have X's on the photograph no longer exist on site. This photo simulates the planned end state of the site. This includes all buildings fully decontaminated and demolished. It assumes the below-grade portion of the reactor has been disposed in situ, illustrated by that gray oval near the center of the photograph. And I'll give you more information on this shortly in the presentation. All hazardous materials will have been recovered and managed, and any contaminated lands remediated. The site will be graded to facilitate surface water management, and institutional controls and monitoring will be implemented. All waste produced will be disposed in licensed facilities where they exist, or stored until disposal is available. Radioactive waste is being sent to the Chalk River Laboratories facility in Ontario that I mentioned earlier, where CNL is attempting to establish a low-level waste disposal facility. In addition to the main laboratory campus, which I've been sharing with you so far, the Whiteshell Labs also has a dedicated waste management facility where waste produced on site has been stored since the site was built. This includes two main areas. If you look to the bottom middle left, you see the concrete canister storage facility, which includes 16 above ground concrete storage silos for spent fuel that was the result of the WR1 reactor operating. CNL will be transporting this high-level waste to Chalk River for centralized storage until a national repository is sited and built. The other section that takes up most of the rest of the photograph is simply called the waste management area. It contains various waste disposal and storage structures that range from low-level clay-lined trenches, the grassy areas you see there, to concrete bunkers, to concrete below-grade silos, and other storage methods. All waste, except possibly some of the trenches, will be recovered, characterized, segregated, packaged, and managed appropriately. The waste types and conditions vary greatly through these storage structures. All radioactive waste is planned to be shipped to Chalk River Labs for storage and ultimately disposal. Once all waste is removed and the waste structures themselves are demolished, any impacted soil will be remediated and institutional controls and monitoring will be implemented. Part of CNL's responsibility in conducting the decommissioning and the environmental remediation is effective public and Indigenous engagement. CNL works with First Nations in Treaty 1, Treaty 3, and Treaty 5 territory. Our site is located in the traditional homeland of the Métis Nation. Historically, the relationships with Indigenous nations was pretty weak or frankly non-existent in some cases. So CNL has been working hard to correct this and has ongoing relationship agreements in place that support initiatives such as community liaisons that work more closely with CNL. We conduct joint environmental monitoring, and we've been incorporating traditional knowledge into our programs. The photo shown here shows the Saugeen First Nation Community Liaison Committee, comprised of elders, youth, and other members touring the WR1 reactor. A couple other photos just to share here. In the upper left, CNL is exhibiting at the Manitoba Métis Annual General Assembly. In the bottom left and the upper right, a Métis monitor is working with our environmental techs, collecting mushrooms for analysis and collecting groundwater samples from our extensive network of wells. And the last photo, again, giving a tour to members of Black River and Hollow Water First Nations inside the WR1 reactor. So now we'll dive in a little bit to exactly what is decommissioning. So decommissioning is a pretty complex process that involves many types of engineering. CNL's first priority is always safety, and that begins with hazard assessment. We're pretty passionate about safety for workers, the public, and the environment. But the main decommissioning process always follows the same typical path. Planning starts first. This includes preparation of decommissioning plans that identify hazards, identify waste and waste disposition pathways, and the methodologies planned to actually perform the work. Next comes characterization. This is a comprehensive evaluation of the decommissioning target, a building or some other structure, identifying locations and types of radioactive materials, hazardous materials like lead and asbestos, and industrial hazards like energized systems. The next step is hazard removal, including deactivation of all energized systems and decontamination. Typically, impacted systems are removed from buildings to achieve a clean or near clean state. This enables demolition to occur. And as I mentioned previously, all waste is properly managed and packaged. A few photos to share of some projects. These are different types of characterization work going on. We typically do physical, chemical, and radiological collection. This might be scanning with instruments, taking physical samples, performing analysis. Sometimes we have historical waste packages that have not been well documented, and we have to determine the best method to sample those and determine waste disposition pathways. Waste hazard removal and system removal. This can be anything from remediating non-radiological hazards. We have vast amounts of asbestos in our buildings based on the times they were built. So typical first activities include asbestos abatement. Then we'll have selective removal of components and systems that have been impacted in other ways, sometimes by radiological work. And then we will conduct de-energization. Here, the photo on the right shows excavation of piping systems and typically electrical systems that are entering buildings underground so that they can be properly isolated. So overall, decommissioning means carefully characterizing and then removing and managing all waste. And I mentioned some of these, but characterization looks for radiation, asbestos, lead, mercury, chemicals, and other hazardous materials. Once the building is fully de-energized, and it makes it safer to remove the hazards, and then it enables us to begin full building demolition. Building materials, including concrete, wood, insulation, roofing, structural steel, rebar, are all segregated Oftentimes, we're able to recycle metal when we can demonstrate that it is non-impacted. Other materials will go to landfills for licensed, where licensed appropriately, or as I mentioned, get shipped to Chalk River if contaminated. After demolitions are complete, surveys are done to ensure soil is clean. If it's not, any remediation is done. And then typically backfill of the excavation happens, topsoil is applied, and a grass mix is planted. That is the typical decommissioning process. Ultimately, our business could be boiled down to waste management. I mean, we are really producing waste. So in conducting the decommissioning environmental remediation of the Whiteshell site, overall, CNL's is estimating we'll generate close to 5,500 shipments of sealands or other kinds of shipping containers of clean waste, including metal for recycling, 350 shipments of hazardous waste, such as non-radioactively impacted organic materials like roofing tar, and around 2,000 shipments of low-level radioactive waste, and up to 600 shipments of intermediate level waste. These are just different waste categories based on the characteristics of the material. Transportation of waste is safe and very effective. On the slide, you can see what we've accomplished to date. 6,700 cubic meters of low-level waste sent to Chalk River from Whiteshell, and all of this has been done with 0 incidents and 0 accidents. To give you a little bit of deeper dive into what it means to decommission, I'll present to you a few past, present, and future projects. The CNL team completed the first major nuclear decommissioning project in Canada on the Whiteshell site. This wrapped up in about 2016. This involved the decontamination, deactivation, and demolition of 85,000 square feet of radionuclide laboratory space, known as Building 300 on the site, if you recall back to the early photo. This building housed many laboratories, workshops, and offices for the multitude of research projects. Constructed in stages from the 60s to the 80s, this building presented a variety of hazardous materials that were safely overcome. As I mentioned, the use of asbestos-containing materials is widespread. Laboratories are also equipped with dedicated drainage systems for nuclear materials, and this network of glass and stainless steel piping had to be carefully segmented and removed. Over 190 fume hoods were removed and dismantled, and the radioactive ventilation system was thoroughly characterized. Fixatives were applied, and then ducting was segmented and removed. All impacted systems were either decontaminated or removed from the facility for waste management. The building contained many energized systems, electrical, air, water, etc. These are all de-energized to ensure hazardous energy was completely removed. This, in our industry, we call this air gapping typically. Final clearance surveys were done to the entire inside and outside of the building. Then the big iron went to work, methodically demolishing the building, segregating the waste, taking it down to the bottom of the crawl space where the cavity was backfilled with clay, and the end state is a nice grassy field. Another really interesting project on site is the decommissioning of WR1 reactor. This historical photo I'm showing you here shows the excavation that was made to take down the overburdened soil to bedrock. It's a little bit difficult to see, but in the bottom left middle, you can see a crane in one of the tiers of the excavation, and then in the very bottom, there's a tractor in there. So this was a fairly large excavation, and it still absolutely amazes me. This reactor was built in 18 months during the time period 1963 to 1965. So it was designed, constructed, commissioned, and began operation in less than 2 years. It operated for 20 years through to 1985, where it achieved the extent of its mission, and it was safely shut down. I mentioned it before, but it was designed to test the concept of organic coolant instead of water. This was an operational benefit in that you could operate it at lower pressure and higher temperature. And while it worked great, this was not the prototype model that went on to become the CANDU reactor fleet that is used around the world to generate power. WR1 also tested various fuel materials and configurations. Overall, it was a pretty small reactor. It had a nominal output of 60 megawatts thermal. That would be the equivalent of 20 megawatts electrical, though it never produced power. It was never configured to do so. It was strictly a research reactor. It is a extremely robust building, and it is built 5 stories below grade. So the picture I showed you earlier of the reactor doesn't really give you true indication of the facility. On the left-hand side, what you see is a cutaway of that building, showing the reactor systems located in the 5 stories below grade and some of the above grade structures. This is an interesting project because CNL does not have a disposition pathway for some of the waste from this reactor. There simply is not a planned or anywhere near term option to dispose of the reactor core components. Now, all of the reactor has been already prepared for decommissioning. All the fluids have been removed. The fuel has been removed and is safely stored in the canisters on site. We basically have an empty facility that has activation from the operation of the reactor. So we are proposing something called in situ disposal, which is a combination of the demolition I described on the previous project and conversion to a permanent disposal facility. Ultimately, this is achieved by demolishing and disposing all of the above ground structure. And the disposition pathways include recycling, landfill, and any impacted waste going to Chalk River. We would prepare the below ground for grouting. Basically, we fill the below ground area with a highly flowable concrete grout. It penetrates large ducts, tanks, and pipes, which we will cut holes in before, and we will also cut holes in floors to enable air to escape as we backfill it. The grout is really there to provide a stable macro-encapsulated space. It's not really there to prevent groundwater movement, but it does provide additional benefit in that way. Next, we'll fabricate a concrete pad over top to ensure the waste is effectively isolated and contained, and that it's not easy to access either on purpose or by accident in the future. On top of that, we'll build an engineered cover system to manage water as well as frost, animal ingress, and plants. And then we'll implement institutional controls and post-closure monitoring, which is proposed for 100 years. This project is not approved yet, actually. It's in the environmental assessment and licensing phase. But this model that you see on the right-hand side kind of shows how it relies on multiple levels of barriers to isolate and contain the waste. Over 99% of the radioactivity resides in the very center core components, which is labeled as a reactor core. That's a stainless steel can with stainless steel and other material fuel channels. And the safety case is ultimately based on the fact that those materials are in very stable metals that will take a very long time to corrode and therefore be available for transport, and therefore they can decay safely. Another really interesting project and a very challenging project is what we call the stamp pipes. This goes back to our waste management area. So the stamp pipes were fabricated at the waste management area. There are 171 concrete tubes of varying sizes and construction types. They're all installed below grade, approximately 4 meters deep, and they were used to store higher activity wastes through the 1960s and even up into the early 1990s. Unfortunately, the waste was often first placed in something like a paint can or a garbage can and then dropped into these stamp pipes. The stamp pipe was then backfilled with sand, and most of them have a bitumen seal at the top as shown in the diagram here, and many of them have a permanent concrete cap. Some of the later standpipes were fabricated with removable caps, but these are, there's less of these than the permanently sealed ones. The waste records are incomplete, although somewhat good, and the waste is certainly expected to be degraded by corrosion. Some of the materials in these are known to produce methane and hydrogen, so they create other hazards that we have to deal with. So CNL, along with some key subcontractors, has designed a fully remote waste recovery, characterization, segregation, and packaging system. This bespoke equipment is currently being fabricated and will be transported to the site in 2023 for assembly, commissioning, and deployment. There's several massive units that perform specialized tasks. One unit is designed to open and vent the standpipes, another to exhume the waste, and a third, called the sorting and conditioning unit, performs the waste characterization, sorting, and packaging. That unit exceeds 1 million pounds, and it will be moved around using mobile jacks. These units contain various remotely controlled and operated tools, with operators a safe distance away, controlling everything with cameras and force feedback controllers. Once fully mobilized, the project is expected to take about 3 years to complete. Protection of the environment is one of CNL's top commitment and a condition of our license, frankly. CNL has an extensive environmental protection monitoring program. The three main components provide all kinds of data for the Whiteshell site contaminant pathway monitoring, enabling the monitoring of contaminant levels in the environment. This includes effluent monitoring, which is both water and air, environmental monitoring, and I'll give you some details on that shortly, and groundwater monitoring. And our site is highly characterized, both the soil and the bedrock. CNL tries to be highly transparent about its monitoring results. We provide public access to the annual safety reports. And as I mentioned, we're very interested and open to having people come on site and work with our monitoring team to see exactly what we're doing to monitor our performance and protect the environment. The impact by CNL is extremely small, typically orders of magnitude below threshold levels. Some of the examples of regular monitoring conducted on and near the site includes upstream, downstream, and adjacent to the site measurements in the Winnipeg River, including the water, sediments, and fish. We do surface water in ditches. So we regularly collect and analyze that. We get soil samples on site and from nearby locations, including nearby farms. We get garden produce produced by the public, and we analyze that. We will collect wild game that has been killed in road collisions to monitor game in the area. And of course, we do ambient and background radiation measurements. This only represents a subset of the thousands of samples that we collect annually. And as I mentioned recently, we've invited monitors from First Nations and the Manitoba Métis to tag along with our environment techs. This has several benefits: relationship building, confidence that CNL is protecting the environment. And for CNL, we get the benefit of adapting our monitoring system to incorporate Indigenous knowledge. So just to wrap things up now, CNL is conducting one of the largest environmental remediation projects in Canada, and it's located just an hour from Winnipeg. The site and operations are under license by the Canadian Nuclear Safety Commission, the federal regulator, and they conduct regular inspections on us. The government of Canada has committed full funding to remediate this legacy site and effectively decommission and reduce nuclear liabilities. The planned target is to complete site closure by 2028. So CNL, backed by the government, will continue to perform environmental monitoring for another estimated 100 years to just verify that the predictions of our environmental assessment are holding true. So thank you so much for this opportunity to share some of the amazing work that's going on at the Whiteshell Labs. I really welcome any questions, and we will take those on now. Thank you.
Perfect.
Perfect. Thank you, Brian, for your presentation. This is such an interesting and eye-opening session since nuclear engineer is not a very popular topic in Manitoba. So if you have any question you'd like to ask Brian, please type them into the chat. We can start with the first question from Christopher. So what is the final intent for the site? Will it remain secure or closed? Will it become a park or will it be sold off?
Yeah, thank you, C, and thank you, Christopher, for that question. So CNL has prepared a proposed end state for the site, which describes the conditions that we will achieve at closure. And we've been relying on existing categories of site end states that are typically used by the government, residential, agricultural, industrial, et cetera. The vast majority of the site, greater than 95%, is unaffected, is clean, pristine site. We will remediate the remaining site down to those determined end states. We're about to undertake engagement to talk to the public, talk to Indigenous nations about potential future uses. So there is a lot of opportunity to potentially reuse the site, but at this point, there is nothing firm in place in terms of that. It's unlikely to be sold off. There is a possibility of it being transferred to the local municipality to have Indigenous involvement, but those are part of the negotiations that will occur as we start to approach the end state.
Sounds great. So the next question I have is from Wen Wu. So how long will the site be monitored?
Yeah, that's a great question. The current proposal is that we would continue to perform monitoring for about 100 years after closure. Now, this involves a variety of different kinds of monitoring. A lot of it would be based on groundwater monitoring, but there's other aspects to monitoring. It is likely to change over the decades. We'll continue to provide the safety reports related to that. The site will remain licensed under the oversight of Canadian Nuclear Safety Commission, and really they determine the final duration of monitoring. But it is proposed to be about 100 years.
That sounds really, really long.
It is pretty long,
yeah.
And but that's the normal, expectation around the site, and it's based in science and engineering. I mean, we know that for the small amounts of remaining contaminants, we understand clearly what their transport mechanism is, and when we would expect to see, in groundwater, for example, very low levels of transportable materials, that we can verify that the site has properly been remediated and is performing well.
Of course. Thank you for your answer. And I have a question from Michelle. Will the Institute disposal site be marked in the event there is the development at this location?
Yeah, that's a great question, Michelle, and absolutely. So there is both administrative and physical ways of marking, something like an in situ disposal. In the end, it kind of becomes a grassy hill, but there will be deed restrictions in place and on the record so that, someone wouldn't go and dig up the site, for example, and build a building there in 100 or 200 years. But we'll also rely on physical monuments, some sort of very durable physical monument that would mark the location of the site.
Yeah, that's definitely good to know. I think I have another question from Christopher here. So are you allowed to state the total cost for this project?
Yeah, I can give a high level. I mean, this project overall is approximately $1 billion, for the complete remediation, waste management, closure of this entire site. So it's a very large, substantial project.
Yeah, that is definitely cost a lot of
Yeah.
money. Yeah. Um, I have a question from Douglas. So timeline for the approval of implementation of WR1 decommission and ultimate implementation of the plan.
Yeah, thanks for that, Douglas. I mentioned that we're in regulatory approval right now. So we are conducting an environmental assessment, and the Canadian Nuclear Safety Commission, along with a number of other regulatory bodies like Environment Climate Change Canada, Health Canada, the province of Manitoba, they all have to do an assessment. This is expected to take about 2 more years. So around this time in 2024, is the plan to do public hearings on the project where CNL would present its results of the environmental assessment, and there would be an independent commission hearing from interveners about the project. So we could see approval in the very end of 2024 or the beginning of 2025. And if that approval is received, we will be ready to begin work almost immediately. We're doing a lot of the engineering, design, and work planning now. And it'll take about 3 more years to complete that work. So we could finish up in 2027 on the WR1 project.
Yeah, that's still quite a while to go.
Yep, lots of work to do yet.
Yeah. A question from Tricia. So as a part of the environmental performance monitoring, why was groundwater monitoring not included?
Oh, good question, Tricia. It is definitely included. So if I indicated otherwise, my apologies. But the entire site has a very extensive groundwater monitoring network. So we very, very well understand the groundwater conditions, the soil conditions, the monitoring of the speed. We do semi-annual monitoring of groundwater now. We look at levels, we look at contaminants in the groundwater. And so that's all documented and shared in our public safety reports. So certainly groundwater monitoring is a very, very important aspect of our environmental monitoring program.
Great, thank you for your answer.
Yeah.
And I have Richard here has a question for you. What has become the close to site URL facility? Is it really decommissioned?
Yeah, so Richard, you're referring to the underground research laboratory, the URL. And this was a facility located near the Whiteshell site, a little bit northeast, east of Lac du Bonnet. And this was essentially an underground research laboratory that was used by Atomic Energy of Canada and Canadian Nuclear Labs to develop the concept of deep geologic disposal, which is a method that's been adopted by many countries around the world as the ultimate solution for nuclear fuel. So Canada essentially invented that process. Countries like Sweden and Finland are going ahead with facilities now. Canada is working to identify a potential site for a deep geologic disposal facility where nuclear fuel would be disposed of. And so we had built this underground mine at this underground research lab. It was a 420-meter deep mine. No nuclear materials were used there, but what was done was research on the rock conditions, the groundwater movement, the concept to build buffer materials and storage containers. And that work was completed. That research was done. Canada has very well developed that concept. And so we did complete the decommissioning of that site. All of the above ground buildings were removed. The below ground portions of the facility were cleaned and closed. And it's basically under some monitoring now, but there's really no waste that was at that site ever. And so it's basically a closed mine site, I would describe it as.
Yeah, it sounds great. Yeah, thank you.
It was a really interesting place because countries from all over the world would come there to collaborate with Canada to perform research. Basically, every country that had a nuclear program had some involvement. So it was really amazing work that happened here in Manitoba.
Yes, definitely. I have another question from Douglas as well. So can you provide your contact info for the further question or inquiries?
Sure, yeah, I'm happy to do that. Maybe I'll put my email in the chat, and happy to collaborate or talk to people if there's some follow-up questions later on.
Of course, thank you, Brian. I have another question for you. So what are the major risks for the human health?
Yeah, that's a good one. I mean, I mentioned in the presentation that hazard assessment is one of the most important things that we do. So I'm not sure if the question is related to staff that are performing the work or the potential for impact offsite to the public and the environment. So I'll kind of touch on both. And so when we're performing work, the first thing we really do is a very thorough investigation of hazards, radioactive or non-radioactive materials, and we put in place engineered barriers or other kinds of approaches to protect workers from those hazards. So that is the core of our business. We're very good at it. In terms of offsite impacts, I mentioned that our operations have very little impact, but as part of the environmental assessment for the whole site, we have done full fate and transport monitoring, and we have done predictions on potential dose impacts to various receptors. So we look at someone who would build a farm right on the site in the future after presumably government controls fail and there is no longer any controls over the site. So someone builds a farm, grows all their local, grows their own food, farms with animals, fishes out of the river, etc. We also have an indigenous receptor who is primarily a harvester that relies on the land. And so we've done that fate modeling, and happy to share it to anyone that's interested in the details, but our predictions are that we are about 5 orders of magnitude below what is already a very restrictive level of a potential dose. So we know that based on that safety case, the project will be protective of the environment and of people. So I hope that addressed that question.
Yeah, I'm glad to hear that the environmental and the human health is protected. So it's really good to hear. Another question that I have for you is that during this work, have you encountered any significant environment contamination, such as soils from the operations over the years, which requires special cleanup?
Yeah, one that comes to mind right away, we were decommissioning some buildings they're not radioactive buildings. They were, a soil laboratory. We didn't expect to have much contamination or other hazardous materials in there other than some asbestos. So we were performing the decommissioning, and during demolition, when we started to take out the foundation of the building, the workers detected a smell, like a hydrocarbon smell. And so we stopped work and we started to assess what we had found. And there was you could walk to the site and very clearly could smell this sort of fuel smell. It was unexpected. And what we did was we started to look at historical photos. And what we found out was that when the site was built in the 1960s, there was a work camp in that area where workers were living. It looked like there was a couple of above ground fuel tanks that were running boilers. Our suspicion was there was some leak in the past. So some of this diesel fuel or heating fuel got in the ground. And at the time, practice was probably cover it with soil, put clay on top of it. A building got built on it eventually. So we discovered this during the decommissioning, and we went on a fairly extensive soil remediation effort. So we dug a lot of the soil out of the ground to recover that contamination. One of the benefits of our site is it's got a lot of clay soil, so contaminants don't move very far, very fast because of that. So we dug everything out, a pretty substantial number of trucks. I think it was about 130 trucks. And then we've put in place additional groundwater monitoring to see if there is any further transport of that unexpected contaminant, and we've seen nothing so far. So that's one example where you sort of don't know what you're going to expect in decommissioning, and when you discover it, you stop, you develop a new plan, and you put that in place.
Yeah, that sounds pretty interesting at the same time. Pretty scary when you discover that contamination.
Yeah, it's contaminated sites exist all over Canada, and whether it's a gas station or a mine or whatever, the one good thing about this project is the government is committed to fully clean up, and so we've got the resources, and it's a really interesting and rewarding job to work on a project like this.
Sounds great. Yeah, thank you for your answer. Yep. I have a question from Dave. Can you please provide a description of the process of transporting contaminated waste to Chalk River?
Yeah, thanks, Dave. So I described the different types of waste, and so different types of waste require different types of transport containers and different kinds of transport processes. So I'll just touch on a few to give you a taste of what they are. So most of the waste we produce is low-level radioactive waste. It's generally very safe to handle. It has low levels of contamination. What we would do with that kind of waste typically is transport it in a large metal container, typically with a liner in it, like a sealand container. So it could be soil, it could be building debris. We would place that material into that container, and then it would be trucked to Chalk River. And it was kind of subtle, but we don't have a disposal option in place yet, although we do expect to achieve one in Chalk River. So now many of those containers are in Chalk River awaiting permanent disposal. For more other types of waste, so at the other end of the spectrum, used fuel. So I showed you a photograph. We have 16 canisters that hold spent fuel from the reactor. It's very safe to manage spent fuel, but fuel has higher risks. So there are very highly engineered containers that are used around the world. They're licensed by the regulator to enable transportation. Again, it's done by truck, but we use a container that is owned by an organization called the Nuclear Waste Management Organization. It's a government agency in Canada that's in charge of ultimately creating a permanent disposal site. So they have a special container that we use to place the waste in for transportation. So I hope that answers the question. We did look at other methods of transportation, such as rail, but there are some logistical challenges with that. The onloading and offloading of waste onto rail spurs wasn't ideal for us, so we rely on truck transportation.
Sounds good. Yeah, thank you for your answer. I have another question right here. So, do we have remediation measures in place if they have risk to human health based on monitoring data?
Yeah, another great question. Thank you. So I presume this is, in the future, the site is closed, we have monitoring, and then we see something that is not expected, higher contamination, for example, in soil or in the ground. So yeah, absolutely, there are contingencies that have been planned that are well understood. There are engineered approaches to performing remediation if we have to. Highly unlikely that this is the case, but let's say we see an unusual result from a groundwater. So what we would probably do first, because the groundwater moves extremely slowly. So if you remember the picture of the site, from the reactor to the river is about 500 meters. It takes about 100 years for the water to move over that duration because of the groundwater conditions. So we have time. So we would increase the number of samples, the frequency of the samples, the location of the samples. We would verify whether or not it was a unusual measurement or there's something happening there. And let's say in the unlikely but plausible case that there's higher contamination, we would probably build something like a pump and treat or some other kind of curtain wall that intercepts the groundwater and treats it. So those are well understood technologies. They're effective. Like I said, it's unlikely, but yes, there are contingencies in place.
Sounds good. Thank you.
Yeah.
I think this is my own question I have. I'm not sure if anyone was asking the same questions, but why was the Pinoa location chosen for Whiteshell Laboratories?
Yeah, no, that's a good question. Thank you. So I mentioned it was in the late 1950s. So, Chalk River was Canada's national lab, but they were kind of at the point where, the site had reached its maximum capacity there. And so the government was looking at establishing another site to take on new research initiatives, including the reactor, the waste disposal stuff. And so they, basically started to look at, where in the country is a good place. And they looked at where labs didn't exist. And, it was Alberta, Manitoba, one of the eastern provinces at the time. Alberta had the oil industry, number of reasons. So, probably we had a good member of parliament at that time, and they identified the site. Also, the site was very suitable. It had, water for cooling the reactor. It had the right kind of conditions in terms of geo kind of conditions, the soils, the groundwater, the bedrock, etc. So, there's a number of things that went into it, but that's kind of how they selected the site, and that created the laboratories. So it has been a huge contributor to the Manitoba economy and the eastern Manitoba economy from that.
Yeah, it sounds like environmental factors play a great role in this decision. Yeah. I have one last question for you from Glenn. Okay. So was uranium the main in feed? So were other reactive elements used on site?
Yeah, thank you, Glenn, for that. So in the reactor, the main fuel is uranium. But as I mentioned, that reactor, it tested different kinds of fuel configurations. So it used different enrichments of uranium. It also used other radioactive materials like thorium. And so WR1 was instrumental in developing fuels that are in use today at power reactors around the world. But definitely uranium was the most significant fuel in use.
Wonderful. So I think that's all the questions we have for you today, Brian. Thank you once again for joining us today. So do you have any comments before we wrap this up?
Well, great questions. I really appreciate them. Lots of really diverse questions. So thank you. And I did put my email in the chat. I invite anyone that wants to have any follow-up just to reach out to me. So thank you very much for having me today.
Yes, and thank you all for attending this presentation. So did you meet past part of the session? Please don't forget to check out the Ingenium Hub's on-demand library for recordings of this and all of our live sessions, as well as exclusive professional development content. And see you in the next session.
Thank you for watching. Visit the Ingenium On-Demand library for more exclusive content.